The next presentation will be held in English language. Industrial robotics has moved far beyond the static arrangement of fixed robotic arms, which are optimized to be extreme but poorly responsive to change. The management and production of diverse product portfolios can only be achieved with dynamically variable configurations and robots that react flexibly to these. Only a rapidly changing software can provide a meaningful long-term answer to the wide range of problems that arise. This approach raises many questions. How can we make the latest scientific results easily reusable? How can a research institute or even a startup company quickly get access to a new, effective algorithm? These questions will be explored in this talk by Tamás Pepó, team manager at KUKA, R&D Hungary.
Welcome, everyone. Oh, blinding lights, this is what they call. Finally, the presentation is also here. We seem to be a bit sparse than it was with Mr. Simonyi. Probably I'm less interesting, or I at least don't have subtitles, so sorry for that. I will be talking about robotic ecosystems, and this will be today a bit sporty, because I've prepared lots of slides and I don't have too much time actually, so let's jump into the topic that we have. So what is a robot exactly? This is a robot, of course. I think everyone, even though I can't see it, but I think everyone assumes that this is a robot and know that this is a robot, an industrial robot arm from KUKA, by the way. Yes, so this is one of the things that we will be talking about today. The next one is a 3D printer. Is this a robot? Well, of course, this implies the same issues and problems. I mean, the whole 3D printer ecosystems, they have tendentiously the same issues and problems that they have to solve like robots, and they are also operating in factories. So we can, of course, probably talk about these as well. And then washing machines. So there's a definition of a robot, which is either that one or that these are complex electromechanical systems that have an effect on their workspace, so on the environment. Of course, a washing machine does have an effect on its workspace, which is very limited for sure, but I'm not going to go into the direction of washing machines. I will leave it up to Bosch to have it for them. So these are robots, or these could be robotic systems that we were talking about, or at least the two on the right side. And then there's ecosystem. So this was the second word for my presentation. And I had a mini survey with my relatives and friends who are not from the IT. And I was asking, what is an ecosystem? And they were like, oh, the coral reef. Yeah, sure, the coral reef, of course. So I have to put it onto my presentation, the coral reef. Thanks, Google, for the image, by the way. And there's a definition. I hope there are not so many biologists here, so excuse me if there are some. I found this definition that this is the ecosystem is a system in which creatures live in, they interact, they sometimes interact with each other, and in a specific environment. So let's put these three things onto the slides, four things, of course, because this is what we will be having with robots as well. They are somehow interacting with each other. They have the factory as their operating space, sometimes not even a factory, so it could be even broader. They are interacting with each other and in the specific environment. So all of these definitions, they are the same for biological ecosystems and robotic ecosystems, of course on an abstract level. Of course, for robotic ecosystems, we are not playing around with fish or octopus. That would be weird, of course. We are playing with some other things. What we have is like a special combination of virtual and physical things all around. It could be robots there, of course. I put a Yaskawa onto the slide as well, just not to be too biased for KUKA. It could be any robot manufacturer and any robot that we can think of. Of course, there are other physical machines in factory. That's a CNC machine, but you can imagine several more. And that's just the physical layer. So, of course, there could be human interaction and so on, but we are now focusing on machines. So These are the physical ones, and then if you want to integrate them into your ecosystem or into a system that works or that is highly optimal to some extent, then you need to have some virtual tools or software that helps you to integrate, to simulate. So that's what I wanted to show on the slide, that there are usually simulation solutions. And I think there was already a presentation today that emphasized the importance of simulation. So yes, for sure, so the Y and the Z generation, they are just entering the market, so it's even more important to focus on these digitalization things and digital twins. The problem is that you can already see on this slide is that there are lots of ecosystem players, and then this easily explodes. So there's lots of them, and there are lots of APIs, tons of APIs that you have to take care of, interfaces, data models, whatever. So it easily explodes. And then we are at the point where we want to build this in the digital world somehow up, but we want to get more ahead. So we want to be more abstract. We want to achieve something bigger. And what is the heart behind the scenes, actually, of how to reach new heights is the robot operating system. So that is not just for the robot. Usually, robot operating systems they have a basis on which you can create ecosystems, and you can easily communicate with these players. As of nowadays, there are issues with this. So there's tons of APIs that I've already told you. We can easily have a robot shown in a visualizer. We can easily input a robot into a simulator. Of course, it will be very different for different manufacturers. That's one of the problems. We can have different algorithms like the simultaneous localization mapping that was shown by Richard before. Then lots of field bus setup and the whole factory layout simulated. It's quite hard. There's a lot of things coming inside, and you somewhere have to take away the complexity. And that's the main issue. That's the main issue that is to be addressed by the ecosystems. Because we don't want to waste our times with lots of different APIs. We just want to bring it to a more abstract level, and we want to do cognitive robotics. We want to do adaptive robotics. Of course, I'm not about to plan a motion from the smallest increment that I want, because at one level with higher semantics, I'm about to use my robots for the exact task that I'm about to do. And I don't have to know robotics. I don't have to be from a robotics background in order to do so. This is these easy-to-use concepts that most of the manufacturers, as of nowadays, they are trying to bring. So what an ecosystem does, and underneath the robot operating system that supports it, is to bring things to a higher level of semantics. Thanks, Google, again, for this nice picture. So you can imagine it as a bridge that is bringing you over a valley somehow to the top. What's on the top, right? So that could be a good question. That's not blood, before getting accused. That's art, for example. That's from New York, Guggenheim Museum. One of my colleagues in my teams, she has found this picture. There are two authors, and they would like to show this complex behavior of what the machinery has and how it interacts with people. This is just sweeping the blood back, but the blood flows again, so it's like a constant amount of work, let's call it this way. So for our way, so how could we pave the way in order to help people do such things like this, or even, of course, more realistically, for factories to have a complex automation lines or a matrix carcasses that István was talking about last year, my colleague, in this conference, then we have to have something that we can rely on. So, for example, robot operating system. And we'll go deeper into more specific things, or more like deeper into implementation. So There are lots of algorithms, lots of ideas all around the world, like from Australia, Europe, Asia, wherever. And these ideas are usually, so they would, in order to get from Europe to Asia, they need something of a common system, so common constraint system. Then, of course, they will need a lot more. So there are communication patterns available in here that you don't have to think about how two software components should communicate. Of course, you also don't want to think about how to install something. So it's easy to imagine that if I have a new SLAM algorithm somewhere in Budapest, that's not that easy to install probably in Japan, because the people in Japan probably are using different robots, different systems, different OSs. So it's pretty hard to grasp the problem and to be able to spread this new algorithm, which would be of high value and would give you high usability to some extent. And then you have to install it and package it and so on. So in order to be able to spread this algorithm, you need these. Also easy to use. And there's tooling. Of course, this comes hand in hand at some point. If you have good diagnosis tools, if you have good simulation tools, if you have good integration tools, then it's easy. So these are coming from the same topic. So just think of the ideas. So these researchers are having their ideas, so they want to find something that fulfills their criteria of how to spread their knowledge all around the world. And this is where ROS comes into picture. This is an abbreviation for Robot Operating System. Yeah, very good abbreviation. Because this serves as the constraint system. This serves as the operating system underneath the whole ecosystem that we are about to build. And then these ideas are usually software components, probably services in a service-oriented architecture system, and then you want to reuse those. And of course connect them to some point, and then we could be lucky, of course, that this algorithm from Asia is compatible with our algorithm from Europe, and that's finally compatible with the tooling from Australia, and everyone's happy, right? Probably not the case, because ROS is just the operating system and the corresponding tooling around the operating system. The logo of that's what is a robot operating system, because we haven't defined it for now. That's an OS on top of an OS. It brings you the necessary robotic functions that you need in order to move your robot, to integrate your hardware, even to pass messages. But it will not solve the problem what kind of message you want to send around. It just gives you all the technologies through which you can easily send around messages. But just have an example. If you want to throw homogeneous matrices all around, and the other side wants Euler angles and position vectors and so on, then you have to convert. And then you're finally not compatible. Of course, I know it's easy to be converted, but just imagine that you have to convert everything. You are not operating on the level to be explicitly compatible with these modules all around the world. So you have to probably get something else on this software-oriented architecture, because we are now in an aquarium. So you have all these creatures inside. We know that, so that's the place where they should be. But we are just standing there that, I have lots of services, what to do with them, how can I integrate them? This is compatible with the other one, but then the third one that I want to try out is not compatible with the first two, then I have to reinvent the wheel again and again and again. So it's pretty hard. For this, ROS will not bring you in itself the solution. There are approaches, though. Open Robotics Foundation, probably one, or it could be ROS Industrial and ROS2. So there are already two versions of ROS existing, because ROS1 was primarily focusing on the research community, and it exceeded in that. But for industrial usage, you will need something else. You will need stability. You will need real-time control. You will need scalability, which is not there for ROS1. But still, ROS2 will not solve these problems. So there's an initiative, there's a consortium called Ros Industrial, which manages the roadmap of ROS2. So whatever they do, they want to standardize interfaces so that you can easily integrate all of these partners or players in your ecosystem. And then it starts to look like as an ecosystem, finally. Of course, KUKA could be a player there because we are providing robots. Of course, we are providing tooling, which could be compatible with this ecosystem. And there are lots of other possibilities. Why I highlighted that one is that I will talk about a more specific contribution that we have in Hungary for these ecosystems in a few more slides. And then there was Richard, of course, there, with his SLAM algorithm. Which would be best if it would be implemented and integrated into the Ros Industrial ROS2 ecosystem. Then I can easily reuse it. I can try it out. I can do some proof of concept implementations and prove that it really works and use it. That would be the best thing. That's one approach. So you have ROS as a robot operating system, and then there's another big player coming from a very different market, not necessarily open source. It's Nvidia. What Nvidia has, of course, the GPUs. Yeah, I'm not a big player, I have to admit, but I know that they have the best, or one of the best GPUs, of course. But they are already working on solutions for the term they call live collaboration on data, which will eliminate interfacing questions. This will concentrate on semantics of data, and then you can easily reuse in any partner within this within the small ecosystem that Nvidia provides. Nucleus is the core, which provides some functionalities, and there's a lot more like environment modeling. They have the hardware for parallel execution. What they also have is Nvidia Isaac, which is a robotics platform. So Nvidia has taken advantage of their competence in this very good hardware that they can provide. And they have built an ecosystem on top of Omniverse because the simulation that they provide is on top of Omniverse, so you can easily integrate and collaborate on data. The simulation will be out of the box and explicitly compatible with any other tooling that Nvidia provides. And Isaac has lots of algorithms inside. And actually, they have a bridge to ROS2, and they have lots of robots already operating on their hardware, which is called Jetson. So they have lots of variants of this Jetson hardware package, very performant one, because they have these FPGAs, GPUs on their systems, and they have ROS2, so they can expose ROS2 functionality as well, and then they are there. So it's easy as that. Of course not. That's hard work behind the scenes. Let's get even deeper into implementation, so I will focus on one specific topic of what I was showing you, and this is exactly this hardware interface thing that I was telling you about. That KUKA could be providing such an interface in order for the KUKA robots to be easily usable based on the ROS Industrial standards in ecosystems like ROS2 or Nvidia Isaac. And this is what one of my teams is actually working on in Hungary in an advanced development project. In order to understand what is happening here, this is a generic stack of a robot operating system, particularly the motion part of that. So there's, of course, a high-level planning. There's an interpolation in the middle, and there's control. And down there, you actually have the hardware. So 3 layers, probably sometimes it's just 2, it depends on which system you use, but you can send down the increments and control the robot through a hardware interface. ROS has, with the help of Ros Industrial, ROS has also standardized the way how to interact with hardware, and actually they are having standardized stacks with this MOVE-IT2 and ROS2 control to map this generic structure into their system. And you can easily exchange different controllers. You can easily exchange different mappers based on these interfaces that they provide. And then you just have to take care of your hardware layer on how to interact with your hardware. It's quite the same as in Windows. So there's a driver which interacts with your keyboard. Of course, it's not a keyboard, it's a robot, but who cares? Of course, we care, because it's a slightly more complex. This is the generic build-up. I don't want to show a lot about this. You can find it out on GitHub. This is the ROS2 move it, ROS2 control, and whatever stack. This is just for info. Under the hardware interface, and what we are doing in Hungary actually, is that we are providing an industrial capable ROS2 driver, which is clean, standardized, extendable, scalable, with Ros Industrial standards. That's the most important thing. In order to access our robots, and we are accessing all 3 robots. Okay, we can access 3 robots. What's the importance in here? Because all 3 of them are working on different KUKA operating systems. So it's hidden, completely hidden from the perspective of ROS2 and probably Nvidia Isaac. You can easily use these without knowing what kind of protocol or through which protocol we communicate with the robots. And you can use everything from the previous side, move it to ROS2 control, and whatever you want, with the robots that are the most precise out on the market. You can easily integrate into ecosystems. You can find it actually on GitHub. So, and now, back to the Aquarium, because that's interesting that finally we are looking inside. We didn't know what we are seeing, actually. We didn't understand that. But now we understand. So there are a few sharks, big sharks, like the Titan, which can lift up to 1 ton for a KUKA, or I mean a KUKA robot, or a KUKA LBR Easy, which is a cobot. You can access that without any problem. You can access Yaskawa, ABB, whatever. And not just that, you can access RGBD cameras, any kinds of sensors, machinery that is in factories. And that's what an ecosystem should provide, to be able to collaborate on the level of data, as Nvidia has phrased that. And I hope this is the message that you can bring with yourself home today. That's what I wanted to tell you. Thank you very much for your attention. There are some links to the sources of images, just to be totally concise. Thank you very much.
Thank you for your presentation. We received 3 questions. So I will ask them, what are the most promising applications of robotics in different industries, and what are the benefits?
That's a very good question, because this is not tendentiously about ecosystem, that's about the applications that we have. So one of the most promising areas is cobots, because you can get into the way of cognitive automation. You don't have to put fences around your robots, finally. That's what cobots bring you. And the most interesting applications, aside of let's say, the more traditional, conventional applications of arc welding and so on, of course, these are still interesting to some point. But for the cobots, it opens up the whole space of the factory. You can also have AGVs going around, which take the human presence into account. And this is the actual direction in which we are trying to go, and also other ecosystem partners are trying to go, to not necessarily focus on one specific application, but rather to help this barrier that we have to step over to get into robotics. So there are lots of people who want to do very new applications. So it's not about the traditional applications. That's now about some new stuff already. Like I think in the factory of Audi, they're already having one of the robots that I've showed you that are measuring the distance between 2 plates, for example, whether that's inside a limit or not. And there are no fences around. So the workers can just easily interact with the robots, and they will not get harmed.
That's interesting. Thank you for your answer. We have another question. What are the ethical and legal issues surrounding the use of robots, and how can they be addressed?
Well, That's a very interesting question because I had thoughts in this direction before as well, that we are selling robots, lots of robots, which could be seen as taking away jobs. Yeah, it could be seen in that way. But with the first industrial revolution, so people were like, okay, there are new machinery, it will take away our jobs. It didn't happen. These jobs have just transformed, changed into something different. And that's what this revolution, so industry, the fourth industrial revolution, we are now experiencing more or less that. We are even through the third one, actually, to some researches, but we haven't realized. So this is just the fourth one. Probably the fifth one is also coming. And so there are different jobs, for sure, now than as it was in the beginning of the 90s. But is it a problem? So do we want to still get stuck on the level that we were 100 years ago, or do we want to step up and go to a higher abstraction level? That's the question that I'm throwing back to the who asked this. But thanks for the question. That's very important.
Thanks for the answer. And our last question that we received, what are the current trends in robotics and how are they shaping the future of automation?
Yeah, trends. So trends is the ecosystem. And that's the biggest trend that we can think of. And all the tooling, all the simulation, everything, that's in the ecosystem. Everyone wants to build some kind of an ecosystem in order to lower this acceptance barrier of robotics. That's the exact trend. And you can do it with cobots, of course, because if you have a cobot in a small factory, you have an idea that you could automate. Yeah, for sure. Okay, but how? You have to buy a huge KUKA robot and then buy a lot for the integrators, or pay a lot for the integrators to integrate your robot. So you're getting nowhere. But the trend is that you will be having a robot which you can easily set up, you can easily interact with, and then you can integrate yourself. So it's a quick proof of concept. But this is also coming with the existence of ecosystems. This is the same thing. Digital twins, I know that there were a few words already told about digital twins before. That's also one of the trends. But this is also, for me, this is an ecosystem question and a robot operating system question, which is below the ecosystem. Because you're interacting on the level of data with digital twins. And in order to optimize, because we as humans, we tend to optimize to a local minimum or maximum. It depends on the use case. So your everyday life, even myself, so we are tendentiously optimizing on a local manner. If you would be about to optimize on a global level, then we would be much more ahead. But with these tools, you can easily optimize on a global level. I mean, at least on the factories level, or even more factories could be connected, and then you can get the most out of the system. And this is the trend. This is what. So it's not just about, okay, we have lots of data and we throw it at you, and then you do whatever you want with them. Because this is where big data is stuck right now. There's lots of data, but what to do with that? Okay, you can do whatever you want, but what and how? And that's the next thing that we want to conquer with our robotic ecosystems, to optimize on a global scale.
Thank you for your presentation and answering our questions.
Thank you very much.